Today in this lecture we discuss about a priori probability. In this lecture we discuss what is the statement and proof of a priori probability, and then we find the relation for priori probability. Now first we see what is the statement of priori probability. A priori probability is also known as a postulate of equal a priori probability, and it states that all accessible microstates corresponding to given macrostate are equally probable. Or in terms of probability, it also states that the probability of finding the phase points in any given region of the phase space is identical with that of another region of equal volume. And that statement we prove here. For that, we consider a phase space. In that phase space, we choose the two cells. That cell we call I and J, both having same volume. And 5 phase points we choose, those are distributed in these two cells. That's R, A, B, C, D and E. Now, we firstly find how many possible macrostates and their corresponding microstates we get by arranging 5 phase points in the two cell. For that, the number of phase points in each cell denoted by Nj, and number of phase points in J cell we denote by capital Nj. Therefore, the number of possible macrostates corresponding to these two cells are first macrostates, which corresponds to 5 0, second 4 1, third macrostate 3 2, fourth one is 2 3, fifth 1 4 and sixth 0 5. Since that macrostate which specify the number of phase points in particular cells. Then what are its corresponding microstates? Microstates which specify the place of individual phase points in the particular cells. For considering the first macrostate 5 0, there are only one possible microstate. Since the ith cell which contain 5 phase points, J cell is empty and there is only one possibility of the microstate, and that is 1. In the similar manner, now other macrostates corresponds to number of possible macrostates. In that way, we have to getting if 5 phase points are distributed in two cells, then these two cells, within that two cell we get 6 macrostates, and total number of possible microstates are 32. Hence microstates are 32. Now how we get the 32? For each macrostates, the number of possible microstates we calculate for one of the case of that macrostate 4 1. There are 5 possible microstates. How we get? Since 4 1 macrostates, 5 possible macrostates, we consider the two cells I and J cell. If ith cell which contain 4 phase points, that 4 phase points are A, B, C, D. Remaining one is in the J cell. Since in J cell there is only one phase points. In that manner, we arrange the other possibilities and we get 5 possible microstates corresponding to a given macrostate 4 1. Similarly, we calculate how many possible microstates we get for other macrostates. Here, if the phase points are continuously shifting between the two cells, there are 32 possible microstates and corresponding 6 macrostates, means each macrostate are equally probable. All microstates are equally probable. Now that means each of the microstates which appear frequently. For example, for a given macrostate 50, there is only one possible microstates. Same one microstate we get for another macrostate 05. That means that one of the microstates which appear frequently after long period of time. Now then find how we calculate the priori probability, and that priori probability is equally probable. For that, the priori probability we define the number of desirable microstates for a given macrostate divided by total number of microstates. Hence, priori probability for one of the macrostate we firstly calculating here. Here the macrostate 50. Now what is the priori probability? We possible microstate is 1 out of 32. Therefore, the priori probability for macrostate 50 is 1 by 32. Similarly, for sixth macrostate 05, there is again one possible microstate. Hence, the priori probability is possible macrostate 1 divided by total number of microstates 32. Since first and sixth which having same priori probability. That means each macrostate share 1/13th part of microstate. Hence we say first sixth macrostate is same, priori probability is same, and it share 1/30 part of the microstate. Similarly, for other macrostates, second and fifth, the possible microstates are 5. Hence, the priori probability for that macrostate is 5 by 32. That is again same. Therefore, that microstates are again appear frequently. Hence, for second and fifth, they again say that the priori probability is again same for that macrostate, and they share 5 by 13th part of the macrostates. Similarly, third and fourth macrostates, it also corresponds to 10 by 32 part of the microstate. Hence, we say that if the probability of finding the phase points in any given region of phase space is identical with that of another region of same volume, that means all microstates are equally probable. Nextly, we find what is the relation for priori probability. For that, we considering a large box. That box is divided into number of cells, each cell having area A1, A2, A3 up to the kth cell. Kth cell area is AK. All cells having same volume. All cells which having same volume. Now we find the probability that a ball falls in ith cell. If we suppose n balls which are thrown inside the box, then we find the probability of a ball that falls in ith cell. That probability is priori probability, and it gives the area of that cell divided by total area of the box. What is AI? AI is the area of ith cell, and total area is A1 plus A2 plus A3 up to AK. In the similar here, that relation which shows as the area of the cell is greater, then greater is the probability of finding the ball in that cell. If the area is same, the probability should be equal. Now we suppose instead of single ball, if the two balls falls in the same cell, then its priori probability is Gi into Gi, that is Gi square. In that way, if Ni balls falls in ith cell, then its corresponding priori probability becomes Gi raised to Ni. Now we find for any particular distribution of n balls among the kth cell, then that means if n1 balls which are found in first cell, n2 balls found in the second cell, n3 ball found in third cell, and so on, then the priori probability for the particular distribution of n ball becomes G is equal to G1 raised to n1 into G2 raised to n2 plus into G3 raised to n3 up to the Gk raised to nk, where n1, n2, n3, n4, this gives the number of balls in each cell. Therefore, total number of balls, we write n1 plus n2 plus n3 up to nk, that equal to summation ni, that is capital N. Now we suppose if size of all cells is same, means area remains same, then the priori probability should be same. Now how we get it is same? Now using that relation, G equal to 1, 2, 3, that all cells having same area, means that is 1. We can write here G raised to n1 plus n2 plus n3 up to nk, and that summation sign n1 plus n2 plus n3 up to nk, that gives summation ni or capital N. Therefore, the relation becomes G is equal to G raised to N, and that equation represents a relation for a priori probability. Hence, the probability of finding the distribution of balls in a given box, it based on its priori probability, and that priori probability which depends upon now what is the size of each cell, that gives the relation for priori probability. Hence, in the today's lecture, we discuss about a priori probability. That priori probability, its statement is given all accessible microstates corresponding to given microstate are equally probable, or probability of finding the phase point in any given region of phase space is identical with that of any other region of equal volume, and that we prove using the example. If the two cells having same volume and 5 phase points are distributed in that two cells, then each of microstates appear frequently as another. That means all microstates are equally probable, that we prove here by the priori probability for each macrostate we calculate, and that priori probability for first and sixth macrostate is same, similarly second, fifth is same, similarly third, fourth is same. Hence we say that all microstates are equally probable. Then we find what is relation. That relation we find by using the concept. If we consider the large box, that box is divided into number of cells, all cells having same volume, and in that box, if n balls are thrown inside that box, then we find now what is the probability of a ball falls in ith cell. Similarly, 2 balls falls in ith cell. In that way, if ni balls falls in ith cell, the priori probability we write Gi raised to ni. But for particular distribution of n balls among the kth cell, the priori probability becomes G equal to G1 raised to n1, G2 raised to n2, into g3 raised to n3 up to gk raised to nk. If all cells having same size, then priori probability must be same. That relation gives g equal to small g raised to n, and it gives the relation for priori probability. Thank you.